SwayamPrabha. Digital India. Educated India.
सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 10 and our ongoing series on mechanical measurements. If you recall, in the lecture number 9, we were introducing the fundamental ideas of thermometry. The basic idea was to describe how to come out with a temperature scale which can be repeated or replicated. It required the use of different thermometers to cover different ranges, and I was explaining that there should be some overlap between different instruments which are going to be used to measure the temperature depending on the ranges. And what we will do now in this lecture is to start with complete that discussion, and then we will go and look at or take a look at an overview of thermometry, which consists of just describing, without going into too much detail, the different types of thermometers which can be used, and then we will start taking up one by one for a detailed study. The first one which we will take up in this lecture would be the thermoelectric thermometer, or the use of thermocouples to measure temperature. To recall what we were doing in the last lecture, we were talking about several different thermometers being used to cover the entire range of temperatures from the lowest about 0.01 degrees Kelvin to the highest about 100,000 Kelvin. That was the range which we mentioned, and we said that it is not possible to cover the entire range with using a single thermometer, and therefore it is essential to have different thermometers. We also introduced the concept of a single reference point or the single fixed point for thermometry, which was the triple point of water. We also described in some detail the functioning of a constant volume gas thermometer, and we indicated how it can be used to define temperature as a ratio of pressures. So, we will start from there, and now what we are trying to do is to see how to use or how to measure using different thermometers and obtain values which are in agreement among each other. This was what was explained in the last lecture. For doing this, we require certain number of subsidiary or secondary fixed points, and those fixed points are given in the tables which you see now. The fixed points corresponds to equilibrium states, and the subscript 90 here, for example, I say T subscript 90 Kelvin. That means that this temperature which is assigned in this table is according to the International Temperature Scale 1990. The third column gives T90 in degrees Celsius. That means that this is the corresponding temperature corresponding to T90 Kelvin in Celsius units. So, the various fixed points which are used for thermometry are given by the triple point of hydrogen, which is assigned a value of 13.8033, which corresponds to minus 259.3467 degrees Celsius. Then we use boiling point of hydrogen at 250 millimeters of mercury, which gives a temperature of 17 Kelvin or corresponding to minus 256.15 degrees Celsius. Then boiling point of hydrogen at 1 atmosphere corresponds to 20.3 Kelvin or minus 252.85 Celsius. Then as you go along, you see here several other fixed points like the triple point of neon, Ne stands for neon, which is 25.5561, triple point of oxygen 54.3584, triple point of argon 83.8058. So this is, if you look at the table, the temperatures are going in the ascending order. From the lowest value of 13.80, we have come up to 83.80 Kelvin or minus 259.3467 degrees Celsius to minus 189.3442, and we need more fixed points to cover the entire range of interest to us, and they are given in the next slide. So the fixed points to cover the higher temperature range are given in this slide. Triple point of mercury, triple point of water. In fact, if you recall 273.16 Kelvin, triple point of water was considered as the first with a single fixed point for thermometry. Then we have melting point of gallium, which is about 29.7646, which is very close to room temperature, normal room temperature. Indium, freezing point of indium, about 156.559. Then freezing point of tin, freezing point of aluminum, and the freezing point of silver, which corresponds to 961.78 degrees Celsius or 1234.93 Kelvin. So if you look at the fixed points we have, there are several fixed points covering the range from the lowest temperature to the highest possible, and in fact there are temperatures higher than this which we have not included here. We will come to that in a little while from now. So the ITS 1990, which is a modification of IPTS 1968, the International Practical Temperature Scale of 1968. ITS 1990 includes some modifications. Some of them are minor, some of them are more important modifications. Of course, we will not go into the history of these things. What the ITS 1990 does is to provide the secondary fixed points which are given accurate and acceptable values of temperature as given in the previous two slides, and then it also specifies how to use these fixed points and what kind of instruments you must use to determine the temperature. That is what the ITS 1990 is doing for us. For example, between 0.65 Kelvin and 5 Kelvin, T90 is defined in terms of the vapor pressure temperature relations for helium 3 and helium 4. So using this vapor pressure temperature relationship for the helium 3 and helium 4, we will be able to cover the range between 0.65 and 5 Kelvin. This is one of the lowest ranges. And between 3 Kelvin and the triple point of neon, which corresponds to 24.5561 Kelvin, it is defined by helium gas thermometer, the constant volume gas thermometer, which uses helium as the thermometric substance, and it is calibrated at 3 experimentally realizable temperatures having assigned numerical values. Actually, you will see if you go back to the previous one, 0.65 to 5, and here we have 3 to 24. Therefore, there is an overlap between the two. That means that I can calibrate this with respect to the other one by using this overlap, which is going to cover the two ranges in a certain portion. And it also specifies what kind of fixed points have to be used, and what is the interpolation procedure that has to be used. It is also specified by the ITS 90. And between the triple point of equilibrium hydrogen is hydrogen occurs in para and two forms, and the equilibrium hydrogen contains the two forms of hydrogen in the equilibrium proportion, and that is what we mean by triple point of equilibrium hydrogen, and it is 13.8033 Kelvin. And the freezing point of silver, which is the highest temperature we saw, 961.78, this entire range is defined by means of platinum resistance thermometer calibrated at specified set of defining points and using specified interpolation procedures. That means, we are covering the entire range from the lowest, which was the 0.65 Kelvin, to the highest, which is 961.78 degrees Celsius, by using different thermometers and different procedures for making them agree with each other by using suitable interpolation formulae. And above the freezing point of silver, which is 961.78 degrees Celsius, T90 is defined in terms of a defining fixed point of that silver point and the Planck radiation law. Planck radiation law relates the emissive power of black body radiation with temperature by unique relationship, and that becomes the definition of the temperature that is above the silver point. So, basically ITS 90 is giving us a method by which thermometry can be practiced. It tells us about the fixed points which have been given, assigned some specific numbers, which came out of large amount of experience gathered over a long period of time. And it also tells us that different thermometers have to be used, and therefore, the legitimate question is, how do we make a thermometer? What kind of a process is involved in that? And in summary, by looking at what we have discussed in the last 1 hour, we can immediately say that properties that vary systematically, in fact, that is how we started the whole thing, properties that vary systematically with temperature may be used as the basis for any thermometer. And in fact, several are going to be listed below, and we will look at one by one in the order of their importance, order of their applicability, and the order in which they are found to be used in practice. More often you find thermoelectric thermometers used, and therefore, I have taken that as the number 1. So, the thermoelectric thermometry consists of the use of thermocouples. We will come to it in a little while from now. It means use 2 wires of different materials, make a junction between them, and subject the junction to a temperature different from you have essentially two junctions, one which we call as the measuring junction, the other reference junction. If the temperatures are different, you generate an EMF, and that EMF is the thermometric property, and there is a unique relationship between this EMF and the temperature. The next one is the use of electrical resistance as the thermometric property. There are 2 types of electrical resistance thermometers. The number 1 is resistance thermometer, which uses materials like platinum, copper, nickel, etc. If you take an element of copper, a platinum in the form of a coil, and change the temperature of the coil by subjecting it to an environment of whatever temperature we want to measure, the resistance changes with temperature. Actually, the resistance increases with temperature, and this increase with temperature is characterized by a regular relationship, and that relationship becomes itself the basic interpolating formula for the platinum resistance thermometer. In principle, we can also use copper, nickel, and other materials also, as long as we standardize them and we characterize the relationship between resistance and the temperature unequivocally. The other kinds of electrical resistance thermometers are called thermistors. These are actually semiconductor materials which consist of manganese, nickel, cobalt oxides, and mixed in proper proportion with proper binders, and these can be made into very small elements, and the resistance of the thermistor element is a very strong function of temperature. If you remember, I said the resistance thermometer which uses platinum as an element, the resistance actually increases with temperature. In the case of thermistors, the temperature variation is actually the opposite. So, if you increase the temperature, the resistance decreases rapidly. The difference between the platinum resistance thermometer or the first type and the thermistor is that the thermistor is extremely sensitive, and it can be used over small range because the resistance change is very rapid over a small range of temperatures. It is very sensitive, but the range is limited. In the case of platinum resistance thermometer, exactly opposite. The resistance change is very slow or very small. The rate at which it changes with temperature is very small, but it can be used over very large temperature range. If you recall, in the ITS 90, we use essentially the platinum resistance thermometer to measure the temperature from triple point of hydrogen. You can go back, we can go back to the slide and see what we did there. Between the triple point of hydrogen 13.8 and the silver point 961.78, actually we are using the platinum resistance thermometer as the specified thermometer to cover that range. Therefore, you see that the range is very large, 13 to 961, but the change in resistance is not very large. Therefore, it is not very sensitive in that sense of the term, but it can be used repeatedly to cover a large range of temperatures. The third one is which uses thermal expansion. In fact, we know that most materials will expand on heating, and the change in the volume can be used as the thermometric property, and in fact we have several of them. The liquid in glass are very common. For example, we use mercury or other organic liquid. For example, some organic liquids are used, and it is taken in a small capillary with a bulb. The bulb is a reservoir to hold the material, and the capillary gives an amplification to the change in volume in terms of the length. So, liquid in glass thermometer or liquid in metal thermometers are very common, and these are used in day to day practice. We will not be considering too much detail this, because this is not very, there is not too much of a detail which one has to know. There are other thermometers like bimetallic thermometers, which actually is made by taking two different materials having two different coefficient of expansion and then placing them together intimately, and then of course when you subject it to a temperature, one of them will expand more and the other one will expand less, and therefore the element, if it is straight to start with, will start bending, and when it bends, the amount of bend can be a measure of the temperature. It can also be used in many applications. It can be a thermal switch. When it bends, it will make or break a contact, and therefore it can be used as an electrical switch also. That means that a preset temperature, it will it will open the switch, and yet again when it cools back, it will remake the contact, and so on and so forth. We can also measure, instead of measuring the volume directly, we can confine the material to a constant volume or take it in a rigid vessel, and when you increase the temperature, the pressure is going to increase, because you are not allowing the expansion of the liquid to take place. That means you are converting it to a pressure, and pressure can be measured using a pressure transducer or some such arrangement, and therefore thermal expansion basically consists of three different types of instruments which are given here. And if you remember or recall the ITS 90, we said that above the silver point, temperature is measured using the radiation or the black body radiation law, which is basically Planck's radiation function, and in fact a radiation thermometer uses what we call as a pyrometer. In fact, later on we will describe more fully the pyrometer and how it works, but right now it is sufficient to understand that pyrometer, the basis of the pyrometer is comparison between the source or the target whose temperature I want to find out and the temperature of a black body which has got a certain match between the two. We will describe it more fully later on. The other advantage of radiation thermometry is that there is no contact between there is no probe, and therefore there is no contact between the measured whatever we are measuring temperature and the system whose temperature we want to measure. That is an advantage in this particular case. There are also special methods like spectroscoping methods, laser based methods based on fluorescence, for example, interferometry and so on. These are somewhat advanced, and maybe we will just have a little bit of time to touch upon this. We may not be able to consider them in great detail in this particular course. I am just giving it here for the sake of completeness. So, with this background, we can now look at different types of thermometers. The first type, which we are going to describe in some great detail, is the thermoelectric thermometry or the use of thermocouples, and let us just look at what we are going to do, the way we are going to arrange this particular topic. The thermoelectric thermometry uses 3 distinct effects which have been found to occur, and these are given here. The 3 effects are labeled as Seebeck effect, discovered by T.J. Seebeck in 1821, long ago. Then we have the Peltier effect, discovered by Peltier in 1824, and then we have the Thomson effect, discovered by William Thomson, who became later Lord Kelvin in 1847. So, thermoelectric thermometry uses these 3 effects as the basis for the thermometer. So, what we would like to do is to describe the fundamental effects or the basic effects which take place, and we call it thermoelectricity fundamentals. I will work this out on the board. Then we will describe or define or tie all these 3 effects together by what are called Kelvin relations. These relations are between the 3 effects, Seebeck, Peltier and the Thomson effects, and the 3 effects are described in terms of 3 coefficients, the Seebeck coefficient, the Peltier coefficient and the Thomson coefficient. And the Kelvin relation, what it does or what they do is to give a relationship between these 3 quantities. After understanding these Kelvin relations, we will be able to actually look at how to construct a thermometer using a thermocouple, and that is what we are going to do. Practical ideas about thermoelectric thermometry will follow once we have understood the Kelvin relationship and how to construct a particular thermocouple circuit, and the basic ideas will follow from that. So, what I will do now is to terminate this show and go to the board, and let us look at the fundamentals of thermoelectricity. So, thermoelectricity basically involves the 3 effects I mentioned earlier, and before we go into the details, let me just mention what are the things that happen in the case of thermoelectricity. Thermoelectricity means thermal and electrical phenomena or processes are interrelated. Let me just classify these into 2 types of processes. One, we will call them as reversible processes. The term reversible is being used in the thermodynamic sense, and there could be irreversible processes. So, I am just going to label them first. I am going to discuss what are these different processes and then look at the details. So, let me just recapitulate or talk about the reversible process. The reversible process are the 3 effects I talked about earlier. So, the reversible ones are the Seebeck, Peltier and Thomson effects. The irreversible ones are, we have a production of heat due to a current flowing in a conductor. It is called Joule heating. This is because the conductor will impose a resistance on the flow of electricity, and therefore, there is a irreversible conversion of electrical energy to heat. This is called Joule heating. And the second one is thermal conduction or heat conduction. Thermal conduction in the presence of temperature gradients. That means, if the temperature is varying within a material from position to position, there would be irreversible transfer of heat from a high temperature region to a lower temperature region. So, these are the irreversible ones and these are the reversible ones. What we are interested in studying is this or these effects, assuming that these are negligible, not there. Okay. Of course, in practice the irreversible effects are always going to be there and they will of course create some problems for us, as we will see later on. So, let us look at these three effects, the Seebeck, Peltier and the Thomson. Let me consider two materials A and B. They may be either metal or alloys, but they have to be two different materials. And let me just consider a simple circuit where we have the two materials connected to form two junctions, and let me just write the two wires. This is wire A and I have shown a junction deliberately by a blob there, and this is material B, and this is temperature T1, this is temperature T2, T1 not equal to T2. And if I maintain a current in this loop by having some source of power like a battery connected, which I am not showing because it is of no importance to us right now, I have maintained a current through this circuit and some interesting results take place. So, one, let us look at the direction of the current. It is shown by the arrow which is shown here. Here actually the electrons are moving in the opposite directions. This is the flow of electrons. Conventionally the current direction and the electrons flow direction are opposite each other. Suppose the temperature T1 is less than T2. Suppose T1 is less than T2. The electrons are moving here like this, and in this case they will be moving in the opposite direction. So, in the case of flow of the electrons in this direction, heat is either absorbed or rejected. Heat is absorbed at the junction here and heat is released. This is called the Peltier heat. So, if you have electrons crossing over from one material to the other material at a junction, the heat is absorbed at this junction, for example, and it is some heat is released at the junction with temperature equal to T1. Of course, if I reverse the direction of current, that means instead of this direction, if I change the current direction to this direction, the electrons will move like this and move like this, and the heat rejection and absorption, the directions will be interchanged. That means wherever heat was absorbed in the first case, it will be released there, and in the other case it will be rejected. Okay. So, the heat absorption or the Peltier heat which is absorbed at the junction as the current is maintained, the direction of the current determines whether the absorption or release of heat is going to take place. That is why we call it a reversible process. Reversible absorption or rejection of heat or rejection. This is the Peltier effect. So, the Peltier effect or the Peltier heat depends on the materials A and B. So, the Peltier effect depends on the two materials A and B, and it is found that the rate at which heat is absorbed or released is proportional to the current and proportional to a coefficient called the Peltier coefficient or Peltier EMF. So, the power absorbed or rejected of course, I have explained already that absorption or rejection will be dependent on the direction of the current, and therefore, the power absorbed or rejected is given by dq Peltier by d theta. I am going to use theta for time, because T will be used for temperature. I am going to use theta as the time quantity. This will be given by pi, which is a function of the two materials AB and the current I. Okay? And in the case of two junctions, heat will be, we can go back to the previous drawing here. The current is moving from, or the electrons are moving from B to A here, and here it is moving from A to B. Okay? So, at one junction it is going to move from the material B to A, and at the other junction it is going to go exactly the opposite, and therefore, at one junction there will be absorption of heat, at the other junction it will be rejection of heat. Of course, that depends on the temperatures. So, keeping this in mind, we can say that if you have two junctions, the potential, as you can see, this is the unit is voltage, because the rate of doing work dqp by d theta is nothing but the rate at which heat is absorbed or rejected, is equal to I into, this must have units of voltage. So, this is called the Peltier voltage or Peltier EMF, and therefore, I can say that the Peltier EMF net, I will call it as net, must be equal to pi AB at the junction at temperature T1 minus pi AB at junction T2. Whichever is positive, whichever is negative, that automatically will take care of the signs. So, the net Peltier EMF generated or involved in this process of absorption of heat and rejection of heat is given by the simple formula, which I will label it as 1. So, let us look at what else is going to happen. So, we have considered the Peltier heat, and now suppose I take a single element A. Of course, in the previous sketch we had a B material also connected to form two junctions. I am taking one of them now, and I am maintaining a current through that, and this end is at T1, this end is T2, and if you just go back, you will see that T1 less than T2. Let us just keep it like that. So, T1 less than T2, the direction of current is this, that means the electrons are moving in this direction, electron flow. This is a material of this is A, which is assumed to be a homogeneous material and is in the form of wire for our particular purpose. Now, the electrons are moving from a region of higher temperature to a region of lower temperature. So, they will release heat, give out heat. Okay. When the electrons move from a temperature region of higher temperature to a region of lower temperature in a homogeneous conducting material, heat is rejected if it is from higher temperature to lower temperature, whereas heat will be absorbed if it is moving, the electrons are moving from this side to that side. The same amount of heat will be either rejected or absorbed depending on the direction of the electron flow. Of course, the electron flow direction is exactly opposite the direction of the current. So, in this case, we will say that the heat rejection dq Thomson divided by d theta and it depends on the entire length of this conductor. It is an integrated effect over the length of the conductor. So, I will say this is equal to I times integral T1 to T2 or T2 to T1 some coefficient which I will call it sigma A, which is a characteristic of the material of the wire A, and this is called the Thomson coefficient. I will call this as equation 2. Now, I can in fact go back to the earlier sketch. In the earlier sketch, I had two materials A and B to form a complete circuit, and now we can see that it is for this part of the circuit, this is the amount of Thomson heat which is involved. Similarly, the amount of Thomson heat will be involved with the other leg of the circuit. Now, you notice that if the current is moving in this direction in this A, if I complete this one, the current will be moving in this direction. That is, in one material it is moving from a low temperature to high temperature or high temperature to low temperature. In the other part of the circuit, it will be exactly doing the opposite. Therefore, just like what we had in the case of Peltier effect, if heat is rejected along the length of the conductor A, it will be rejected along the conductor B. So, it will be a difference of similar terms, and therefore, I can write the second equation as dq T by d theta, I will call it net, is equal to the difference between the two, I into integral T1 to T2 sigma A minus sigma B dt. This we can call as 3. So, we have actually described the two effects when we have a circuit made up of two dissimilar materials connected in this form shown here, and there is a current maintained in the two circuits. Here there is a current flowing through the circuit. Now, let us look at what is going to happen if I do the following. Suppose I take the same circuit, this is made of material A and this is made of B, and I am going to introduce a cut. That means that there is no current. There is no current. It is observed, again T1 and T2 are the two temperatures. It is observed that a potential difference will appear across the cut. This is called the Seebeck voltage, and that is going to appear across the cut. So, we will call this Vs as the third quantity or fourth quantity. So, Vs is the fourth quantity which is going to be involved. Now, let us go back and just see what happened. In the first case, I had a current and I had the complete circuit completed. Some amount of heat interaction took place at the two junctions as well as along the length of the two wires. Now, when I make a cut, introduce a cut in one of the limbs of the circuit, it may be either here or in the wire B or wire A, whichever you cut, it does not matter, only the direction of voltage may be different. A voltage will appear, and therefore, this voltage must be related to the two effects we had earlier. Those two effects are not now manifesting as an appearance of a voltage across the cut, and therefore, I can just write using the conservation of energy principle that the voltage which is due to Seebeck effect, when I make a cut, the voltage which is appearing is Seebeck voltage, this must be the sum of the Peltier voltage and the Thomson EMF or the Thomson voltage. And we already have expressions earlier. So, this will be pi AB So, that AB subscript I will remove, I will not use now because we know what we are talking about. So, I will say pi at T2 minus pi T1, this is the Peltier, plus integral T1 to T2 sigma A minus sigma B dt. We will call it as equation 5. So, the relationship between the Seebeck voltage, so we can just write here the Seebeck voltage is related to the Peltier EMF and the Thomson EMF, which would have occurred had we made the complete circuit and allowed a current to pass through that. So, this is an important relationship and it is a starting point for our discussion. In fact, I am going to write it slightly in a different fashion. I will just say pi 2 minus pi 1 to avoid the big subscript and plus of course, the same equation here, sigma A minus sigma B into dt. This is the equation 1. Now, I am going to invoke the fact that the 3 effects are reversible, and what it means is that there is no entropy generation or the change in the entropy is 0, because these are all reversible processes. There can be no entropy generation, and in fact, all I have to do is to find out what is the entropy generation and then put it equal to 0 and find out what that particular relationship is going to give me. Before we do that, let me just introduce another quantity which I call as the Seebeck coefficient. In fact, it is known by different names. It is also called the thermoelectric power. It is nothing but the derivative of Vs with respect to temperature. So, we will say that dVs by dt is equal to alpha, which is a function of A and B, and in general I will simply write alpha because we know that it is a function of A B. Instead of explicitly mentioning that, I will just simply say alpha. dVs by dt equal to alpha defines the, I think this was equation 7, I think, or is 6, okay, this is equation 6. So, actually what I can do is now defining dVs by dt as alpha. Let me just digress a little bit and try to give a meaning to this. Suppose I have the following circuit. This is A, this is B, the Seebeck of voltage is going to appear there. Let us say this is T and this is a T plus delta T. So, dVs by dt is nothing but the elemental, there is nothing, you can see that there is a very small difference in temperature between junction 1 and junction 2. The voltage which appears will be delta Vs, and the ratio of delta Vs to delta T as delta T tends to 0. So, delta Vs or delta T as delta T tends to 0 is your alpha. So, we say that the Seebeck potential per unit temperature difference is nothing but your alpha. This is just a useful way of describing the Seebeck effect. Now, let us look at the entropy generation which is going to take place in such a system, if it were to take place. we are going to of course say that the entropy generation is 0. Entropy change is due to all the heat interactions. Okay. So, I can find out what are the heat interactions. I know the Peltier heat at the two junctions and the Thomson heat all along the two conductors. These are the ones which are going to give rise to the change in entropy, and I am going to require that the change in entropy, net change in entropy must be equal to 0. So, we will write the expression for that. Before we do that, let me write also the previous equation. I think it was given in 7, I think. Equation 5, I will write it for a small difference in temperature between T1 and T2, just like what we did just now with respect to the Seebeck coefficient. So, what I will do is I will rewrite the equation in the form of, before we do that, rewrite equation 5 in differential form. If you remember, there is an integral appearing there. I want to write it in the form of a differential. That means, I have a small difference in temperature between the two junctions. That means that the Peltier effect is due to small temperature differences at the two junctions, and the Thomson effect is also due to small temperature variation along the length of the wire, and therefore, the differential form will be given by dVs by dt. I have to take the derivative of that expression with respect to temperature, which we have defined as alpha. If you want, you can explicitly say alpha AB. This is given by d pi by dt plus integral. When you differentiate with respect to t, it becomes simply sigma a minus sigma b, or dVs is equal to d pi plus sigma a minus sigma b into dt. I think this is 8. So, we have the equation, and let us now write the appropriate expression for the change in entropy. So, entropy change, I am invoking the fact that these three are reversible processes. ds equal to 0, and ds itself can be written as the heat is absorbed at one of the junctions at temperature T. So, the entropy change is pi by T. Pi by T is pi is the absorbed or rejected divided by temperature at that junction, and the other junction is T plus delta T dt. Therefore, I can say that the entropy change is d of pi by T for a small temperature difference between the two junctions plus sigma a minus sigma b into dt divided by T, of course multiplied by I. This is equal to 0. This is because we have a junction at T, this is at T plus delta T, pi divided by T, pi divided by T plus delta T, and therefore, the difference between these two is nothing but this quantity. Okay. So, that is how it comes out like that. So, now there are two equations. I think this is equation number 9. From here, you notice that sigma A from 9, sigma A minus sigma B into dt is equal to minus t into d of pi by t. And I will put this into the earlier equation, which related the Seebeck EMF to the Peltier and the Thomson EMFs, and therefore, I can, for example, if I go back, I have got the expression 8 dVs equal to d pi plus sigma a minus sigma b into dt, and what I have now done is to, I have got sigma a minus sigma b dt from here. So, I am going to just substitute it there, and after some simplification which can be easily done by the student, we can see the following. So, minus t d pi d of pi by t, I can say minus t, it is 1 over t d pi, 1 over t d pi plus pi d of 1 over t will be minus dt by t squared. I am differentiating it like this. Sigma a minus sigma into dt equal to minus t into 1 over t d pi minus pi into dt by t squared. I am going to put this into the other expression, the earlier expression. So, if you do that, I will just write the final expression. So, I should get d pi by t minus pi dt by t squared, this is what we just now had, plus dVs by dt minus d pi by t equal to 0, and therefore, these two will cancel off, and therefore, these two will cancel off, and 1 t will cancel off with this t, and you see that therefore, pi is equal to t dVs by dt, nothing but t times alpha. I think this is equation number 9. That means that the Peltier coefficient or Peltier EMF is the product of the absolute temperature multiplied by the Seebeck coefficient. This is called Kelvin relation number 1. These are derived by Kelvin, and therefore, the name has come. And in fact, you can go back and see that if I go to the previous expression, sigma a minus sigma b dt equal to this, and now again I can I have already got the value of pi in terms of alpha. So, all I have to do is substitute here, and if I simplify it further, I should be able to get. So, the second Kelvin relation 2 will come, and I will just give the answer sigma a minus sigma b is equal to minus t d alpha by dt. So, we have two relations, Kelvin relation 1 and 2, 1 and 2, and what they do is to relate the Seebeck coefficient alpha or the thermoelectric power alpha, then the Peltier coefficient or Peltier voltage pi, and the Thomson EMF through these two relations. That means that the three essentially are interrelated processes, and they are interrelated through these expressions. And in fact, we will notice that we expect all these to be functions of temperature alone, as soon as we have chosen A and B. This is a very important observation. It looks like it is a very simple and straightforward statement, but it is very important, because once you have two materials A and B, then there is a unique relationship between these coefficients and the temperature. Let me just take a simple expression for Vs. Suppose I take Vs equal to some constant A plus B times T plus C times T squared, where I will take T in degrees Celsius. I will take, in the earlier case, T1 and T2 were there. I will take T2 equal to T, and this I will take as 0 degree centigrade, or the ice point. If I take the temperature T2 as equal to T, and I take the other temperature as a reference value at ice point, then I can write something like this. And the coefficients A, B and C are related to the three effects. So, A, B, C are related to the three coefficients, three effects. So, in the lecture number 11, I will start from here. I will find out what is the correspondence between A, B and C and the three coefficients or three effects we have already talked about, and also I will take an example and find out what these numbers are, what are the magnitudes of these numbers, and how whatever we have described till now can be used to construct a thermometer. That is our basic reason for talking about these different materials and junctions and circuits and so on. We will get back to that in the next lecture. Thank you.